one last piece of probability is talking about something called Bernoulli trials that we're going to model with a binomial, and we'll see what I mean by those things in a moment. Essentially, a trial is a Bernoulli trial if there are exactly two outcomes. By default, we call these success and failure. Success and failure are just the terms we use. They do not necessarily mean that one is good and one is bad. For historical reasons, we just call one success and one failure. The probability of a success is independent across trials. Okay? And that means it also doesn't change across trials. This is true enough as long as we're not pulling out more than 10% of the total population. So if we're flipping a coin over and over again, each of those trials are independent because each coin flip doesn't depend on the previous. If, however, we were to poll every student at Viterbo and poll them, are you wearing a red shirt or not, those would no longer be independent because as we pulled out people who were wearing red shirts, there'd be fewer red shirts left to sample. In the examples you get in this class, that case will always be true. We will never be sampling more than 10%. It's just something for you to keep in mind as we go forward. So let's imagine an example where there's a simple game where you can get extra credit points with a probability of 8 in 20, or no points with a probability 12 in 20. So we call this P, because it's our probability of a success, and say it's 0.4, 8 divided by 20. The alternative, the probability of failure, is Q, and in this case is 0.6. Now, if we want to know the probability of getting a success, a failure, a failure, a failure, and each of these are independent, all we have to do is multiply the probability of getting success on the first times the probability of getting success on the second times the probability of getting a failure on the third, failure on the fourth, failure on the fifth. So this reduces down to p squared times q to the third. 2 p's, p to the 2, 3 q's, q to the third. So for our question of any points or no points, okay, if we want to know the probability of getting 2 people with points first, and then the next people getting nothing, take 0.4 squared times 0.6 to the third, get a value of 0.035. Now this is great, but we can take this a step further by using this binomial model. What if we want to know the probability of only one student in 3 getting any points in this game? Is it just 0.4 to the first times 0.6 squared equals 0.144? Now, because I'm asking you this, you probably know the answer is no. But why is that true? Think about how many ways we could get one success in 3 students. Okay? Imagine something on your desk that you're watching this as the 3 students. Any one of those 3 could be the 3 possibilities of success. So we need to multiply this 0.144 by 3 to get our probability of getting 1 success. Now what about a more complicated example where we want to know the probability of getting 4 successes in 10 trials, or in this case 4 students in 10 getting points? Can you immediately tell how many ways there are of having 4 successes in 10 trials? Probably not. Luckily, there is a mathematical notation that allows us to do this. This is given by something called the binomial model. Okay? This funny looking thing here is pronounced as n choose k. Now if you're searching for this in a year, 5 years, whatever, binomial n choose k will pull up this equation here. We'll break down what it means in a moment. This n exclamation mark means n factorial. N factorial means we're going to take whatever number times 1 less than it, times 1 less than that, times 1 less than that, until we get down to 1. So n times n minus 1 times n minus 2 times ... all the way down to 1. We're going to do the same thing for k, and the same thing in this whole set. Here our n is our total number of trials, and k is our total number of successes. So in our example, if we want to say 10 choose 4, we're going to take 10 factorial divided by 4 factorial times 10 minus 4 factorial, which is 6 factorial. We're going to expand this out. Before we multiply all these things out and get really big numbers, we can do a little bit of reducing. So there's our 10 factorial on the top. On the bottom we have our 4 factorial here, times our 6 factorial. Now what you'll notice is that the 6, 5, 4, 3, 2, and 1 all match up, which which means we can get rid of those. And now we have 10 times 9 times 8 times 7, or 4 times 3 times 2 times 1, which means that there are 210 different ways of getting 4 successes in 10 trials. Okay. So our probability of 4 in 10 is 10 choose 4 times 0.4 to the 4th times 0.6 to the 6th equals 210 times 0.00119, which is about 1 in 4. This is the way we use the binomial model. As a final note about these things on the side, or excuse me, about these rules, these are simply the rules out of the book. I do not expect you to be able to copy these down quickly, but this is a good reminder of where these values are and how we're calculating them. Now you notice there's a value for the standard deviation, the mean. This comes back to our ability to model with the normal or with the Poisson distribution. I will not be asking you on the test to use the normal model here, because all it's doing is taking any mean and any standard deviation. The Poisson, all I want you to know is that if we have very low counts, the normal model will not work. In those cases, we can use the Poisson model instead. Not actually asking you to use it, I just want you to know that it exists and when it might be useful. These are the values. On the test, the only question I will ask you is, if we have a model where the normal does not apply because it's a very low count, what model can we use instead? The answer will be the Poisson model. Okay. Note that spelling, it will be important. Modeling with the normal is something we will come back to after the next exam. It is an important feature, and it's something that's very important for us to understand, but in this case, I'm just going to let you guys read the textbook and go with that.